In this recording, we're going to examine exponential functions graphs. Before we do, let's consider this question. How many pieces of paper are created when you continually tear a piece of paper in half? So if you have a piece of paper handy, grab it. So if I have 0 tears, you obviously have 1 piece. So go ahead and tear that piece of paper in half. Okay, so after one tear, 2 pieces, right? I want you to continually tear that piece of paper in half and record how many pieces of paper result after n amount of tears. Okay, so hopefully you took time to do that. And we can now record after 2, 3, 4, 5, etc. Let's go up to 6 tears. I don't know if you got that far, but so to replay, we had 1 piece of paper after 0 tears, and then we tore it in half. We have 2. We tore each of those 2 in half. We got 4, etc. Okay, so I want you to think about what this graph would look like if on the x-axis I have the number of tears, and on the y-axis I have number of pieces. So think about what shape that would be. Okay, it starts out at 1, then 2, then 4, and then it's growing really fast, right? Each time doubling the number of pieces. So hopefully you kind of have a sense that it's going to kind of cruise up like this and then grow very quickly, whereas at first it was not growing very fast. Maybe it was growing something like that. So that's an example of an exponential function. And we're going to consider exponential functions in this one, a basic exponential function, where we have a b value that is positive. Okay, it doesn't really make sense if b is negative. Alternates positive and negative depending on the exponent. And b can't be 1 either, because then it just stays the same, right? 1 to any exponent is just 1. Okay. So let's have you complete this table without using your graphing calculator at all. Okay, just using your knowledge, fill in all the ones you know, and then look for patterns. Then play the recording when you're ready. Okay, so hopefully you took time, like subbing in numbers. 2 to the 0 power we know is 1, and then 2 to the first is 2, and 2 squared is 4, etc. All right. Now let's work the other way. With no calculator, obviously we're doubling when we go bigger values of x. We are dividing by 2, so that could be half, 1/4, etc. Also using your exponent rules, 2 to a -3 is like 1 over 2 cubed, right? You remember that. So go ahead and plot those points, play the recording when you're ready. Okay, so that's the graph of 2 to the x. As we thought, right? As we thought with our paper folding, that it would behave like that, it would grow quickly. So now I'm going to have you continue by graphing half to the x. You might say, I don't know what half to the x is. Well, go ahead and fill in the ones you know. You think you know half to the 0 power, and half to the 1 power, half to the 2nd power, things like that. And then hopefully you can develop a pattern. Play the recording when you're ready. Okay, so hopefully you took time to do that. Anything to the 0 power is 1. Anything to the first power is itself. So if it goes like that, 1 to half, anything squared, well, we square the numerator denominator, so that's 1 over 4. Hopefully you picked up right up on that pattern. That's supposed to be a 4th. All right, and then if we're halving as we go to bigger values of x, as we go to smaller values of x, we double, right? So 2, 4, 8. Go ahead and plot those points. Okay, and that's the graph of half to the x. That's called exponential decay. Don't know if I'm stealing any thunder. I don't think I am. So let's name these graphs. We'll call this one exponential growth. This is exponential decay. Obviously, if the value of b is a 1, it's just going to be a constant, right? It's going to be a horizontal line. If the value of b is less than 1, that means it goes down each time we raise it to a bigger power of x. So that's going to be exponential decay anytime the b is less than 1, but greater than 0. Okay. A couple questions on the back side. I think you can answer the domain and range. Please play the recording when you've done so. Okay, so hopefully you said the domain is all real numbers. And the range, well, it gets really close to 0, but never gets to 0, and then it extends to infinity in the y direction. I'd like to add one more feature of this graph, the horizontal asymptote. If you remember, we discussed asymptotes in our rational function unit. We said that it is a line that the curve approaches. So if you're looking back at this exponential graph, the line that this curve approaches, in this case, when x is very, very small, y is getting very, very close to 0, right? These numbers are getting half as big each time. And then as we look at our exponential decay function, as x gets very large, these numbers are getting half as big each time. And so this is getting closer and closer to 0. It will never reach 0, but now we can say that our asymptote is the line y equals 0, which corresponds to the range, how this value here cannot equal 0, but it gets very close. Are these one-to-one functions? Think about that for a second and play the recording. Well, yes, they are. They pass the horizontal line test. When we look at the tables, each y value has exactly one pre-image, right? So, in other words, if I told you the number of pieces, you would be able to tell me how many tears that we had made. So, this is a one-to-one, and we can tell because it passes the horizontal line test. What that means about the inverses is that their inverses are going to be functions. Thanks for watching.